In the last few lectures, we were examining unidirectional transport in a curvilinear coordinate system, specifically in a cylindrical coordinate system where one of the coordinates is the distance from an axis. So, this can be used, for example, for transport in a pipe or a cylindrical object where the surface of the object is a surface of constant coordinate if the coordinate is the distance from the axis. And we had done a balance equation for this coordinate system, if you recall, and we had got a conservation equation, okay, of this form. As you can see, the differential operator here is slightly different from that in a Cartesian coordinate system, and that is because the surface area of a differential volume changes as the coordinate changes. Okay. And therefore, you get a slightly modified form of the operator in this case. And we had also seen for a fluid flow, if the flow is in the axial direction, then the equation is identical to what we get for mass and energy conservation, except you substitute the velocity, axial velocity for the concentration or temperature and the momentum diffusion coefficient instead of the mass or energy diffusion coefficient, the body force per unit volume instead of the source. If it is in the azimuthal direction, okay, if it is around the axis, then you get a slightly different form of the equation, and this we were not able to derive. I just stated it because it is not within the scope of this course. And then we looked at steady solutions. Okay. For a steady solution between two temperatures Ti and To at radius Ri and Ro, the solution for the temperature field is given by log of R by Ri. Okay, this is effectively ln of R by Ri by ln of Ro by Ri. Okay. That is what the temperature field is for a steady temperature with 0 at the inner surface and 1 at the outer surface. So, if I scale the temperature such that the temperature is 0 on the inner surface and 1 on the outer surface, this is what I get for the temperature field. We had got the heat flux. The heat flux was proportional to 1 over R. Okay, the heat flux was proportional to 1 over R. The cylindrical surface area of any surface around the axis, okay, the cylindrical surface area of any surface around the axis is proportional to R. Therefore, the total heat transfer rate is independent of radius, in this case for steady transport, because there are no sources or sinks within the differential volume. And we had got this as the heat transfer rate. Okay, we had got this as the heat transfer rate. Okay. So, the total heat transfer rate, okay, I will just write it again here, this is minus 2 pi L k into T naught minus Ti by the natural logarithm of R naught by Ri. Okay. That is the expression for the total heat transfer rate. Okay. For a tube of length L with inner radius Ri, outer radius Ro, inner temperature Ti, outer temperature To. Okay. And we also got the heat transfer resistance, okay, the heat transfer resistance, which is minus of delta T by Qr. Okay, the change in temperature for a series for two tubes in series, the change in temperature across the inner tube delta Ti by Qr is the resistance of the inner tube, and for the outer tube it is delta T of the outer tube divided by the heat transfer rate. Note that this is the heat transfer rate, it is not the heat flux. Okay. The heat flux does depend upon the radius. The heat transfer rate does not depend upon the radius. Okay. So, for the heat transfer rate, we can just define the total heat transfer rate as the difference in temperature times the sum of the resistances. Okay. sorry, I should define it the other way. Okay. So, this q r is equal to T naught minus T I, okay, and with a negative sign, okay, with a negative sign, and the sum of these two resistances. Okay. So, for a series the resistances will be added up. Okay. For a series the resistances will be added up as shown over here, okay, as shown over here. Okay. And therefore, q r has to be equal to this times this inverse. Okay. Kindly note this correction, there should be an inverse over there. Okay. q r, you recall, is like a current, difference in temperature, recall, is like a voltage difference. Okay. Voltage difference by current is equal to the sum of the resistances. Okay. And therefore, when you get the flux, you have to take the difference in temperature and divide it by the sum of the resistances in order to get what is the flux from the temperature difference between the outer surface of the outer wall and the inner surface of the inner wall. So, we were solving a problem, a practical example of a cylinder, a flask, okay, of height 0.1 meters. Okay. Inner diameter was equal to 4 centimeters and the outer diameter was equal to 4.2 centimeters. The region between the inner and the outer cylinder of the wall was filled with vacuum with thermal conductivity that is 2.4 into 10 power minus 3. Okay, this is about 10 times less than the thermal conductivity of water. And initially you pour in water at a temperature of 100 degrees centigrade. Okay. The initial temperature is equal to 100 degrees centigrade in of the water. Okay. Okay. Outer temperature is equal to 25 degrees centigrade. And what we would like to find out is, if you maintain it at that outside temperature, what is the time taken for the temperature of the flask, of the water in the flask, to decrease to 50 degrees centigrade. Okay. So, that was the problem. Okay. So, the final temperature is 50 degrees centigrade. Okay. So, we are trying to find out what is the time taken. Okay. What is the time taken? Okay, in this case. And here we will assume that since you have an insulating material on between the inner and the outer wall of the flask, since the material is insulating, the heat transfer resistance is in that material between the inner and outer surfaces, and therefore, the rate of conduction within the liquid inside itself is much faster than the conduction across the wall, and therefore, the temperature of the water inside the flask is a constant at any instant of time. This is an approximation. In real systems, you will also have convection currents within the flask, okay, and those have to be taken into account. However, if the conductivity of the wall is sufficiently small, you can assume that most of the resistance comes from the wall, and therefore, the temperature of the water inside is approximately a constant. The change in energy of the water has got to be equal to the total heat transferred from the water to the outside through this wall. We will assume for now that there is no conduction through the end caps. Okay. If there were conduction through the end caps, then this would be like a parallel resistance. There is one conduction through the end caps and one through the cylindrical surface. Okay. So, you would assume a parallel conduction model in order to solve this problem. In this particular case, we will assume that there is no conduction across the end caps and there is only conduction through the cylindrical surface. Okay. The rate of change of energy of the water, m Cp times temperature of water by dT is equal to minus of the total heat transfer rate, okay, is equal to minus of the total heat transfer rate. And if you recall, the heat transfer rate was given by negative of 2 pi k L into the outside temperature minus the water temperature divided by the natural logarithm of the ratio of radii. Okay. With the QR was negative of this, since the rate of change of energy is equal to minus QR, you get a positive sign on the right hand side. And therefore, I get dT W by dt is equal to 2 pi k L into T naught minus T W by m Cp ln of the ratio of radii. Okay. I can write this as minus of T W minus T naught by a characteristic time. Okay. What is that characteristic time? T c is equal to m Cp ln of Rho by Ri by 2 pi k L. That is the characteristic time. Okay. And to evaluate the characteristic time, I have to determine what is the mass of water, we know what is the specific heat, and we know what is the length of the cylinder. Okay. So, the mass of water has got to be equal to pi into T square by 4 into H into the density rho. Okay. Pi d square by 4 is the cross sectional area into the height is the volume into the density is equal to mass. Okay. The density of water is given by 1000. Okay. The diameter is given by 4 centimeters. Okay. So, this is equal to pi into 4 centimeters 0.04 meter the whole square by 4, okay, into the height, which is 0.1 meters, into the density, which is 10 power 3 kg per meter cubed. Okay. And you can do this calculation and you will get this as 0.126 kg. Okay. That is the mass. So, I substitute this in this expression 0.126 kg into Cp is 4.2 into 10 power 3 joules per kg per degree centigrade into log of R0 by Ri. R0 is 0.021 by 0.02. Okay. The diameters are 4.2 and 4, therefore, the radii are 2.1 and 2 centimeters. Okay. So, you have the same dimension in the numerator and denominator as you should when you are taking a logarithm. Okay. The whole thing divided by 2 pi into k is 2.4 to 10 power minus 3, okay, in watts per meter per degree centigrade, okay, into L is 0.1 meters. Okay. And if you look at the dimension of the numerator and denominator, ultimately you will get joules divided by watts, which has the same dimension as time, okay, because watts is joules energy per unit time. Okay. And you can do this calculation to get this as 1.7 into 10 power 4 seconds. That is the time constant. Okay. Now, so with this time constant, I have to solve this equation. This is the characteristic time. Okay. with this characteristic time I have to solve this equation. And the solution is an exponential, okay, dTw by Tw minus T naught is equal to minus dt by Tc. Okay. The natural logarithm of Tw minus T naught is equal to minus T by C plus a T by Tc. Plus a constant. Okay. Therefore, Tw minus T naught is equal to some constant C into e power minus T by Tc. Okay. And we know that at initial condition, at T is equal to 0, the water temperature is the initial water temperature. Okay. At time T is equal to 0, the water temperature is the initial water temperature, and therefore, that implies that the constant is equal to T of the initial water temperature minus T of the outer temperature. Okay. Therefore, the equation becomes Tw minus T naught by Tw initial minus T naught. Okay, just substituting for C in here and dividing throughout by C. Okay. You take the logarithm of this, T is equal to minus Tc ln of Tw at time T minus T naught by the initial temperature. Okay. We want to find out the time at which the temperature is 50 degrees centigrade, given the initial temperature is 100 degrees centigrade and the T naught, the outer temperature, is 25 degrees centigrade. Okay, that is what we want to find out. Okay. Okay. So, this is equal to minus Tc, which is 1.7 into 10 power 4 seconds, okay, into log of 50 minus 25 by 100 minus 25. And you can do this calculation to get, this is approximately 1.88 into 10 power 4 seconds, okay, which is approximately 5.2 hours. Okay. So, this flask is going to take approximately 5.2 hours for the temperature to decrease, okay, from 100 degrees centigrade to 50 degrees centigrade if it is maintained in an atmosphere at 25 degrees centigrade. Okay. So, this is a concrete example of how you can use this heat conduction in order to solve a problem of predicting the time it takes for a certain temperature to decrease in this flask. Okay. Let me solve another problem, in this case regarding a rotating cylinder. Okay. So, if we have, this is a momentum transfer problem of two rotating cylinders. Okay. And if you look from the top, it looks something like this. Two concentric rotating cylinders. Okay. Inner radius is Ri, outer radius is Ro. Okay. The inner cylinder is moving with an angular velocity omega I, and the outer cylinder is moving with an angular velocity omega O. Okay. and what we would like to find out is what is the torque on these cylinders if the fluid has a viscosity mu. Okay. In order to find out the torque, we have to of course solve for the velocity field. Okay. We have to solve for the velocity v phi, okay, in the phi direction around the axis, okay, the meridional direction if you will, around the axis. We have to solve for the velocity field in that direction. Okay. And then from that we have to get what is the stress, and from that what is the torque. Recall that I told you that the equation for the velocity field is rho times partial v phi by partial t is equal to mu d by dr of r of r v phi, okay, and the torque, the stress I am sorry, tau phi r, which is the force per unit area in the phi direction exerted at a surface whose perpendicular is in the r direction. Okay. So, this will be basically the force per area exerted in the phi direction at a surface whose perpendicular is in the r direction. Okay. The constitutive relation for this is mu into partial v phi by partial r minus v phi by r. Okay. Those are the equations that we have to use. Okay. At steady state, of course, the time dependent term is equal to 0. Okay. There is no time dependence. Therefore, I have to solve the equation partial by partial r of 1 by r d by dr of r v phi is equal to 0. Okay. Integrate once, okay, 1 by r d by dr of r v phi is a constant. Okay. I will call that as 2a. Okay. The reason for the factor 2 will become apparent in a minute, and multiply both sides by r. Okay. So, this is equal to 2 AR. Integrate this and we will get V phi is equal to AR square. Okay. R V phi is AR square plus B, which implies that V phi is equal to AR plus B by R. Okay. That is the solution for the velocity. Okay. That is the solution for the velocity in this case. Now, we need to find out the constants A and B from the boundary conditions. The boundary conditions are that at r is equal to r I, the angular velocity is omega I. That means that V phi is equal to r I omega I. Okay. And at r is equal to the outer radius, V phi is equal to r o times omega o. Okay. These are the two boundary conditions. Okay. And these two boundary conditions have to be used to determine what are the constants A and B. It involves some algebra. I will not go into the details. I will just give you the results. Okay. The results are that A is equal to omega o r o square minus omega I r I square by r o square minus r I square. Okay. And B is equal to minus of omega o minus omega I r o square r I square divided by So, these are the two constants. You can substitute these into the equations and substitute r is equal to r o and r is equal to r I, and verify that these two boundary conditions are satisfied, okay, by these equations. Okay. It is just a matter of substitution. what is the stress, okay, is equal to mu into okay, partial V phi by partial r is A minus B by r square, and okay, if you take the derivative of this, it is A minus B by r square, and then I have minus of V phi by r, okay, minus of A, okay, minus B by r square. Okay. So, this is just equal to minus 2B by r square, and I have a factor of mu there, so I have missed that. Okay. So, this is the stress. Note that the stress does not depend upon A. Okay. The reason is because this term A times r, okay, where the tangential velocity increases linearly with distance from the axis, that is just a solid body rotation. Okay. If you had a solid body rotation, the tangential velocity would increase linearly from the axis. Okay. So, this represents solid body rotation which does not have any internal deformation, and because of that the stress does not depend upon r. Okay. Now, what is the torque? So, we had to originally find out the torque. Okay. The torque per unit area, okay, at a distance r, okay, at a distance r, right, the force per unit area is tau phi r, the torque per unit area has got to be equal to tau phi r into r, okay, because torque is force times the distance from the axis of rotation. Okay. Therefore, the torque has to be equal to the force times the distance from the axis of rotation, which is equal to the stress tau phi r times the distance from the axis of rotation r. Okay. That is the torque per unit area on any cylindrical surface around the axis. Okay. And the total torque, okay, is equal to tau phi r into r into the cylindrical surface area, which is 2 pi r l, okay, okay, is equal to 2 pi r l. Okay. And I can multiply and I can substitute this in here. Okay. So, this the r square will cancel out and I will get minus 4 pi mu b. Minus 4 pi mu b, and I substitute for this b from here, okay, and I will get the torque as, so I should have a 4 pi mu l times b. Okay, so 4 pi mu l into r o square r I square into omega o minus omega I divided by r o square minus r I square. Okay, that is the torque that is exerted. Okay, and this torque is independent of the distance from the center, the radius. So, it is the same torque on the inner cylinder and the outer cylinder as you would expect, okay, just from torque balance, since there is no body force within the volume. The torque exerted on the inner cylinder has to be the negative of the torque exerted on the outer cylinder, okay, just from force balance. Since the unit normals are in opposite directions, the outward unit normals are in opposite directions at the inner and the outer cylinder, the magnitude of the torque in both cases is the same. Okay. So, this is a simple example of how you would calculate the torque on between rotating cylinders, okay, that there is a non-zero torque only when the cylinders are not in a solid body rotation. That is, when I have a second term in the equation that is proportional to 1 over r, that is not solid body rotation. In that case alone you have a net torque, and that torque is proportional to the length, the difference in the angular velocities. So, if the two angular velocities are the same, you will get no torque, okay, and it is proportional to the radius square. Okay. So, this is omega I. So, these are two examples of steady state solutions, one for heat conduction and the other for fluid flow, okay, in the azimuthal direction. We will continue this. We will go next on to unsteady solutions, starting with similarity transforms and then proceeding to separation of variables in the next lecture. I will see you then.